Welcome to one of two lessons on applied derivatives. In this lesson, we'll focus on rates of change. Let's begin here. We have this great NBA player from Latvia, of course, but even greater than him is this bicycle. Look at this beautiful bike. Guess what material that bike is made from? Well, that bike is made from wood. This is made by a company, a Latvian company called Materia Bikes, making these very, very expensive but very beautiful wooden bicycles. Really, really amazing. Okay, that leads us into a problem about bicycle production. So it says the total cost, C, for a bicycle manufacturer to produce X bicycles is given by this function. So we have this function and it represents the total cost of making these bikes. And it says X values are in the domain of 0 to 600. Okay, first question. Find the cost of producing the following number of bicycles, 250 and 251. So find that cost. And remember, X represents the number of bicycles, so use the function. All right, you've tried it and you found out that it costs this much to produce 250 bicycles and this much to produce 251 bicycles. So you can see it's a high number, but that's the total cost, right? Okay, next question. Find the actual cost of manufacturing the 251st bicycle. So clearly there's a connection between what we just did and this question. So how can you find out how much it costs to produce that one extra bicycle to go from 250 to 251? What do you do with these two numbers? Okay, I hope the answer to that is clear. You take your cost of 251 and you minus the cost of 250. So you're just subtracting these two numbers. Because if this is the cost for 251 and this is the cost for 250, if you subtract them, you'll find out how much the cost went up for that extra bicycle, the 251st one. And that cost is this much. Okay, so now we know the cost for producing that 251st bicycle. Now do the same thing to find the cost of producing the 551st bicycle. So see if you can figure that out. It's not going to be the same cost, it's going to be different. So what is the cost for producing this one? Take the same approach we just did. Okay, to find that one, we need to take the cost of the 551st minus the cost of the 550th. So you've put both of those numbers into the function and subtract them, and you get this. Notice that when we get to this higher number of bicycles, the cost for that extra bicycle, the 551st bicycle, is less than it was when we were at 251. So as this company produces more bicycles, the cost per bicycle is going down. So the question there is why? Why do you think the cost is not constant? Okay, and some answers to that are there's the mathematical answer, and that is when you look at this function, this is not a line. Okay, the only way the cost would remain the same if we had a linear function, and everywhere you look on the line, you have the same slope, because that's what represents the cost, that extra cost per extra unit. It's a slope, but this is not linear. This is a parabola, and a parabola has a curve to it. So if you follow the curve, you notice it's curving downwards over time, and therefore the cost is going down over time. So that's the mathematical explanation. In terms of business, the explanation is something called economies of scale. As you maximize like your production and what, when you have a factory that's making something and a bunch of workers and machines, if some machines and workers sit idle, they're not being used, then you're losing money. But if you're using everything to full capacity, then your costs will go down because you're being as efficient as you can be with your business. So that's why costs go down as you increase production. All right, next question. It says differentiate C to find C primed. So find the derivative of this function. Let's do that first. Okay, here's the derivative. Check yours. And now find C primed of 250. So in other words, put 250 in here and also put 550 in here. Let's see what you get. All right, notice you get these two figures. There's something interesting here. What do you notice? There's something interesting you should notice. Okay, I hope you notice that these two prices are very similar to that cost of extra bicycle that we found here, very close. And we have those same numbers there, 250 in fact, right? So, and that is not a coincidence. Let's take a look at what's going on here. So we're going to talk about something called unit costs. Okay, again, when we have something that's linear, a unit cost is easy to find. So for example, here's total cost of some business and here's units produced. When we have a line, which can have a linear equation like this one, and we know this one has a constant slope and the slope is 5 here, we can see it in the equation, then we know that the cost for each additional unit is 5 more. So that slope, the constant linear slope, shows us the cost per unit, which is 5. Every time you add a unit, cost goes up by 5. Add a unit, cost up by 5. Add a unit, cost up by 5, and so on and so on. That's for linear things, but most things in the world don't follow linear patterns like that. In our situation, here's the graph of the bicycle function, and the function was this. It's quadratic. We can see it has that quadratic curve to it, but it was on a certain domain, so we don't even see the vertex. It just kind of ends there because the domain set only to 600. So we can see costs are going up. However, when we talk about here, we're talking about the slope here. When we talk about the slope of curves, we're talking about the slopes of tangents. So we take the derivative and we can get the slopes of the tangents, right? So for example, well, let me explain this first. Yeah, so you can see here the costs are first steeper. There's a steeper slope and then less slope and then even less slope. So the costs are decreasing as you're producing more bikes. And that's what we saw with the answers we found. The later bike costs less to produce than the early ones. The early ones cost more, higher slope. Costs are higher here, costs are going up less here. And that has a name. In business, that's called the marginal cost. And it is the cost of each additional unit. So we can find the marginal cost by using the derivative, plugging in the value of x, and then we say that's the cost of that extra unit. And then we go to another point, plug that into the derivative, that's the extra cost for that unit. And that's how that works. Okay, so there you can see the slopes getting smaller over time. Okay, let's apply what we just learned about the marginal cost to this problem here. So it kind of recaps here. In economics, the marginal cost is the cost of producing one more unit. This can be approximated by the gradient of a cost curve, right? So by the derivative. So here's our situation. A company produces motorcycle helmets, and the daily cost function can be modeled as this. So that's the cost function for daily costs, where it says x values are between 0 and 150, and x is the number of motorcycle helmets produced, and c is the cost in US dollars. So they can only produce from 0 to 150 helmets a day, and this function will give us the cost if you put any number of helmets into it. Okay, A, write down the daily cost to the company if no helmets are produced. So what will be their costs if they don't produce anything? Well, if we want to find the costs, again, we just put the number of helmets into our cost equation. So in that case, we're just looking for the costs when 0 is the input, 0 helmets. And that, into the function there, 0 goes in here, 0, oh, I should say 0 there, let me change. Okay, there's the 0 substituted there and there. That means both of these terms become 0, and we're left with just 600. So that tells us the cost to the company is 600. That means even if they're not producing anything, there's still costs. There's costs of running the business and turning on the electricity, having employees there maybe, so on and so on. Okay, B, find an expression for the marginal cost, c primed of x. So again, when we take the derivative of a cost function, we're getting the marginal cost function. So find that function. Okay, let's find the derivative. The derivative is this, 7 minus this. 7 because whenever we have x to the first power and we take the derivative, we're just left with the coefficient in front. And over here, we drop the 3 down, multiply by this, negative 0.001 to get negative 0.003, and reduce the exponent by 1. So there's our cost function. And now it says find the marginal cost of producing 20 helmets or 80 helmets. That means when you produce 20 helmets, what is that cost necessary to produce that next unit? Okay, so you use the marginal cost function and you find the marginal cost when there's 20 units. So you put 20 in there and you get this. That number again means it costs the company $6.88 to produce the next single unit, the next helmet. Okay, how about when we're at 80? If they're producing 80 helmets, what's the marginal cost? Okay, so now you do c primed of 80. You notice it's this. Notice what's happening here. The marginal cost went down. So as they produce more, the cost per unit goes lower. That makes sense, because as you're producing more units, the costs can be spread out amongst those extra units. So now the cost per unit is less. Alright, finally it says state the appropriate units for the marginal cost. So what would be the units for these here? Okay, maybe you came up with that. It's US dollars per helmet, and that's for both of those. And why? Because marginal cost is like a slope of the cost curve. And the cost curve or the cost function here has helmets on the x-axis, number of helmets, and cost on the y-axis. So if we think of that as slope, it's always change in y over change in x. So it's the cost per helmet, right? The y values per the x values. Cost per helmets. So US dollars per helmet produced. Okay, let's look at another one. This is kind of a funny problem, I have to say, but let's see if we can figure it out. It says there's a hammock, and it can be modeled by this function. Notice that this is a parabola, and notice a hammock has this shape of a parabola. So we basically have a function that models this hammock here, and there's that parabola, let's say, okay? Now a mosquito is traveling in a straight line of gradient 11. So imagine there's a mosquito flying by and it has a gradient of 11. Well, that means it's flying very steeply like this, let's say. It touches the hammock at point A, so it touches the hammock at only one point. Find the coordinates of that point. Wow, this is completely ridiculous non-real life problem trying to pose as a real life problem. But anyway, let's have some fun with it. Alright, so there goes the mosquito flying by. There it is. Oh my gosh, that's a big mosquito. And it's flying by at a slope of 11. Okay, we have that there. And you may be thinking, impossible. There's not any mosquitoes that are that size in the world. Well, let me tell you, there are. I'm from Canada, and this could very well be Canada here. And in my province, the mosquito is considered the provincial bird. That's how big our mosquitoes are. They're considered the provincial bird. Can you imagine? Alright, so this could be that mosquito. But anyway, let's continue. So we know the slope of any function. So here's a parabola and here's a slope at a point. And the point here, I think we were told in this problem, at point A, the mosquito passes the hammock right at point A, touches it right there. So we know the slope at a point can be found by the derivative. That's what the derivative gives us, the slope at every point, okay? So if we can find the derivative, then we know the gradient. Okay, so what's the derivative of this function? Well, there's the derivative right here. Okay, by power rule, we get this derivative. So now we know that derivative represents the slope at any point, but we know the slope at this unknown point here. So if we know the slope, we can replace this with the slope. Alright, we know the slope is 11, so we're going to put it right in here. So there's 11 set equal to the derivative. And by solving that, we'll get an x value. We will find out what is the x value. In other words, where is the location when the slope is 11? Because the slope is different at every point on this parabola. So by solving this equal to 11, we can find out what is that precise point where the slope is 11. That point right there. Okay, so when you solve that, you get 2. That tells you when x equals 2, we have a slope of 11. Great, but here it says find the coordinates of A. So now we have the x value, but we need the y value of that point as well. Okay, when we have any point and we have an equation like we have here, we can just put that x value into that original equation and we can find the y value. So let's do that now. So f of 2, so again, we're not putting in the gradient function, we're putting in the original function to find the y coordinate. Put 2 in there here, and we get a y value of 10. So that means point A, that point there, has x coordinate 2, y coordinate 10. Strange problem, but I hope you understood the process there. Okay, here's the practice assignment that goes with these kinds of problems, rate of change. Let's look at number 1 and 2 together, just to get you rolling on the practice assignment. Here's question 1. It says the area of a circle with a radius r is given by this formula. We know that. That's the area of a circle formula. It says find dA dr, so that means find the derivative of the area formula in terms of r. Okay, and then we see r there. So find the derivative. What's the derivative of this? Okay, derivative is 2 pi r, because the 2 drops in front, and then the power is reduced by 1, so we have r. There we go. There's the derivative. So now it says find the rate of change of the area with respect to radius, and that's what this is, the rate of change, area with respect to radius, when r equals 2. So in other words, it's saying, what is the gradient? What is the slope? The rate of change is the slope. Okay, so what is the rate of change when r equals 2? So this is our slope formula, right? The gradient gives us slope, and we're asking, what is the slope? What is the rate of change when r equals 2? So you can put 2 in there, and you will find out the slope when r equals 2, or the rate of change when r equals 2. So when r equals 2, we put it into our derivative, and we get 4 pi. And that's the rate at which the area of the circle is changing when r equals 2. Alright, next problem, number 2. We have the profit made from selling cupcakes is modeled by this function. P is the profit, and C here is the number of cupcakes that are produced. Find dp dc. That means, again, find the derivative of this function, or in other words, find the function that will give us the rate of change at which profit is changing compared to cupcakes being made. So what is the derivative? Here's our derivative function. Alright, we applied the power rule, dropped the 2 down, multiplied it here, and then this 5.6c becomes just 5.6. The 20 is gone. Okay, now find the rate of change of the profit with respect to the number of cupcakes when c equals 20 and c equals 60. So in other words, rate of change, it means find the derivative when c is 20 and 60. So put 20 in here first. When c is 20, when 20 goes into the derivative, we get 3.36. Okay, now find it when c equals 60. Okay, when c equals 60, put 60 in there, and we get a derivative of negative 1.12. Interesting that there's a negative answer here. So that's why question C says comment on your answers. So what do you notice happening here? Like, what's going on? Okay, let's see. At 20 cupcakes right here, the profit is increasing. Okay, the profit is increasing by 3.36 because that's our rate of change there. That's our profit based on cupcakes. But at 60 cupcakes, the profit is decreasing. So 60 cupcakes is too much for this small company to make. When they're making that much, they're actually losing money for every cupcake. They're losing $1.12 per cupcake. Alright, that's how we interpret the results. Thank you. We have one more. You can do it. All that same kind of thinking that we just had, read this problem, and let's see if you can figure these out here. Okay, for A, all we do is put 300 into the function, and we figure out it costs this much for 300. Okay, so the cost of 300 was just 300 into the cost function. We get this. Then it says the marginal cost, and that's what we were just talking about, the cost of each additional unit as you go. So that one is where you find the derivative of C. So it doesn't show it here, but if you found the derivative of that and put 300 into that, we would find out the marginal cost. Because this 1,120 represents the total cost. But this represents that extra cost per extra unit. So that's the marginal cost there. Okay, in C, it says find the marginal profit. So notice now it went from marginal cost to marginal profit. So do we have a profit model here? No, but we have a cost model and a revenue model. And you may remember, revenue is all the income that comes to a company, and profit is revenue minus costs. So you're going to have to do a revenue minus costs and find a new function, the profit function. So do that now. Find your profit function when you subtract those two. And then find the marginal profit. That means take the derivative of that profit one and find that marginal profit at 300 items. Okay, check your work. There's the profit function. And when you take the derivative of it and put 300 into it, you get that marginal profit. So what that tells you is at 300 units of production for this restaurant, they are making €11 extra. At 300, they make €11 for that extra item. So good profit for them. All right, hope that makes